and also I dabble in collisionless shock physics and particle acceleration at shocks. I'm really excited to get going with Interstellar Probe. We have some extremely exciting science to study here, and I've been learning a lot as we've gone along here, especially at this workshop. So I'm going to bring up some slides to just set the scene here for the particles discussion. Can everyone see this?
Yes, we can.
Excellent.
Yes, we can see it.
Thank you. So I'm co-leading this topical group with Matt Hill, who's here, and he's going to be one of our speakers in the session this morning. I am not an expert in these topics yet, and that's why what we're going to do is have 4 of the experts actually speaking to you. But what I'll do here is, like I said, just introduce the scene. What we're talking about are, of course, in situ particles, and by this we're talking charged particles ranging from thermoplasma all the way up through galactic cosmic rays. So I'm going to just show some slides from Pontus's introduction on earlier in the week on Monday, and I've highlighted here really the things that we want to get out of this discussion this morning or this afternoon for our European colleagues. In particular, we're going to talk a little bit about the science traceability matrix that we've started populating and the science questions that are pertinent to these particles. Science operations, we'll talk a little bit in particular about, I think, the model payloads and what we need from instruments. That's really where I'd like to go with the topic group, is start refining some nominal or notional, I should say, requirements for the instrumentation that Interstellar Probe will need to carry for the plasma all the way up through cosmic rays to close properly on the science questions that we're identifying here. Of course, this is a community workshop, so we want some level of consensus. Hopefully there will be some active discussion today. And then, of course, we'll be coordinating all the inputs that we gather today. So this is another slide from Pontus in his intro. I've boxed in here 2 of the major kind of mysteries that we have from the Voyager spacecraft. Pertain to force balance, which is not at all understood based on the Voyager measurements, and that's because there was a gap in one of the critical plasma populations and regimes, energy regimes, as well as, of course, cosmic rays, in particular the acceleration of anomalous cosmic rays and the origin and nature of galactic cosmic rays. So I've highlighted those 2 in particular here. I'll skip over this quickly, but just to remind everybody, we've split the mission into 3 phases just for this discussion. And just to orient you, we're talking the inner heliospheric phase from 1 to 70 astronomical units, outer heliospheric phase extending out to 250 AU, and then the interstellar phase at greater than 250 AU. And we've organized this primarily for the engineering discussion and studies, but also it is pertinent to what we'll be discussing here, since, again, that's just how we've blocked things currently. All right, these are the science objectives. I'm going to breeze through these quickly, but the main point to take away here is just how critical these particle observations are to so much of the mission. And that'll be summarized basically through these next couple of slides. So you've seen all of these already, so I don't need to stress them, but obviously the plasma populations that we'll be measuring with Interstellar Probe are fundamental, right there with the magnetic field, fundamental to the physics of so much of what we want to study with Interstellar Probe. And particle acceleration of energetic particles, superthermals, pickup ions, as well as, of course, anomalous cosmic rays, and getting into just, understanding galactic cosmic rays and where they're coming from. That's all huge to our science here, and really exciting, kind of fundamental questions. So I don't think I need to preach to the choir here too much more about just how important these particle observations are. So these are the 3 science objectives. Really what they kind of focus in on are the heliosphere itself. So these are science objective 1 here summarizes the objectives that we have for the physical processes that shape the heliosphere. The second objective focuses on interactions between the heliosphere and the interstellar medium. So really how the sun and the solar wind are affecting the surrounding very local interstellar medium, but then also how the very local interstellar medium and beyond are affecting the heliosphere, which of course we know is the only habitable astrosphere in the universe as far as we know. And then finally, of course, looking at the very local interstellar medium itself. So the third objective here and set of questions relates exactly to that, to looking out beyond our heliosphere into the very local interstellar medium and understanding our place in space. Now, this is the kind of condensed version of the science traceability matrix that we have a working Google document for. You can see that online. The links have been posted. I think they're on the website as well with the workshop agenda. And what I'm highlighting here is, of course, the 3 sensors that we're talking about in this topic group: the plasma sensor, energetic particle sensor, and cosmic ray sensor. And you can see here, they've been highlighted by, this is the 3 different phases like I just introduced. So you can see that the blocks for each of the instrument types has to do with those 3 phases of the mission. And then where you actually see these things filled in is where those instruments are applicable to the particular questions related to these topics here in each of those 3 objectives that I just introduced. Main point, and I'll zoom in on this on the next slide, main point is that, again, these instruments are critical to so much of the science for interstellar probe, the core fundamental science that we're going for here. We do have of course, the preliminary design of the spacecraft. And you can see here where we have notionally located the 3 sensors at this point. The cosmic rays, we want at least 2, ideally 3 perpendicular telescopes, so that we can actually look at anisotropy in the incoming cosmic rays. Plasma and energetic particle sensors are going to be mounted out on one of these extendable booms. And the reason for that is so that we can get 4 pi steradian coverage. In particular, as everyone knows, with the plasma instrument in particular, solar wind is, of course, coming radially outwards from the sun, and this giant dish is pointed back towards the sun so that we can communicate with Earth as we move further and further out into the heliosphere and interstellar medium. So we had to get the sensors out around that dish, which is why they're on those booms. But just keep this picture in mind for now. Again, this is the current design that we're running with, but we're definitely open to any suggestions on that. I'm not going to go through each of these in detail. These are listed in the science traceability matrix that I talked about. You can see the Google document, the working Google document for that on the link on the website. But as you can see, many of these questions are relevant or even completely based on the sensors that we're talking about here. So this is one of 2 slides on the thermal plasma and particles sensor, the low energy particles. You can see a large number of questions there. Going into the superthermals and energetic particles, this is the list of STM questions that we've identified that are relevant to those energies. And then finally, cosmic rays, the list of questions here. Now, I'm going to hand it off to the actual experts at this point. I hope that set the stage properly, but these are the list of folks that we have who we invited to talk today, and I want to thank each of them for agreeing to share their knowledge with us and their thoughts on what we can do with Interstellar Probe. So I'll send it off to John Richardson right now. I think John is on the line. I'm going to stop sharing my screen, and John, you can take over and share yours.
Okay.
And lead the way. So thank you again, John, Matt, Jamie, and Vladimir so much for agreeing to speak with us today.
Is that showing up?
Not yet. There we go.
Okay.
That looks good.
So Drew asked me to talk about the plasma observations we made and would like to make. And of course, I work with the Voyager spacecraft, so I'm going to be talking mostly about Voyager data. Voyager 1's now at 151 AU, Voyager 2 at 125 AU. We're still getting about 6 hours of data per day at about 160 bits per second. Whereas both spacecraft are now in the interstellar medium. The plasma instrument is located on the science boom, peeking up from behind the antenna. This is a blow up showing that we have 3 detectors looking back towards the Earth, which are ideal for looking at the solar wind, but not so good for looking at the interstellar medium. And we have 1 detector looking sideways, which is our best detector for the interstellar medium, but still not optimally oriented. So this is an overview of the heliosphere from a plasma point of view. Now both spacecraft are in the interstellar medium. The solar wind, of course, we have protons flowing out, mean energy of about a keV, speeds going from 400 to 800 kilometers per second. I should mention that the PLS instrument measures energies from about 10 eV to almost 6 keV. At the termination shock, the speed drops. The compression ratio of the shocks a little bit more than 2, so it drops by about a factor of 2. Throughout the heliosheath, the speed reported by PLS drops from about 130 down to about 60 just before the heliopause crossing. Here we have a flow energy of about 50 eV, which is still fairly easy to measure. Once we cross the heliopause, however, the speed drops, starts coming inward. The flow speed is only about 3 eV, which is much more difficult to measure both by PLS, which has a 10 eV threshold, and any plasma instrument. That's why Stewart and Bale and Bill Kurth were talking about using instruments to measure thermal noise Tuesday, I think. The densities in the solar wind are dropping off as r squared. The lowest density we see out in the outer heliosphere, there's lots of fluctuations, of course, due to changes in the solar source. It's about 2 times 10 to the minus 4. So that's as low as you would want to measure probably anywhere in the mission. At the termination shock, the density jumped up a factor of 2. In the heliosheath, we're seeing densities 5 times 10 to the minus 4 to an order of magnitude larger than that. And of course, once we cross the heliopause, the density jumps. These are numbers measured using the plasma wave instrument on Voyager, 0.04 to 0.12 per centimeter cubed, increasing so far as we go away from the heliopause. Temperatures are actually lowest in the solar wind, fairly close into the sun, 20 or 30 AU. After that, we start adding pickup ions to the mix, and some of the pickup ion energy makes its way to the thermal plasma, causing the plasma temperatures to increase. But the lowest temperatures we see in this region are about 1,000 Kelvin. And at the termination shock, we see a jump in temperature up to as high as about 200,000. Throughout the heliosheath, temperatures away from the shock are about 50,000 Kelvin. Now, we still see very sharp structures in the outer heliosphere. This is a shock occurring a few months before the termination shock crossing. So you still see things on very fine scales. In the interstellar medium, of course, the temperature drops. Based on our measurements, we think the temperature near the heliopause is still fairly high, 30 to 50,000 degrees, but we expect it to drop down to 8,000 as we get further away from the heliopause into the undisturbed interstellar medium. Things we don't measure very well on Voyager are, 1, pickup ions. I think pickup ions, by the time you get to termination shock, are roughly 20% of the total plasma. New Horizons is measuring these right now at about 50 AU and doing a good job of characterizing them. Alpha particles we measure on Voyager out to about 20 or 30. Sometimes we see them farther during high CMEs when the densities are higher. But in general, the fluxes are too low after 20 or 30 AU for us to detect pickup ions. And same with electrons. Electron energy in the heliosheath itself, we think is at less than 3 eV. Given our 10 eV threshold, we're not seeing them. In fact, we don't see many electrons outside of roughly 20 AU, except when we have large shocks. So this is something else that Voyager hasn't been able to measure very well, and hopefully ISP can. Moving onward, I talked about pickup ions a little bit, and then we want to measure them because they dominate the thermal pressure of the plasma outside of about 20 AU and in the heliosheath. They have many effects. One is this decreasing the solar wind speed as you add the pickup ions to it. The other, as I mentioned, is that the temperature increases outside of about 20 AU due to the effect of the pickup ions being added to the flow. The other thing it does is change the shock dynamics. When we cross the termination shock, this shows the energy per proton. If I showed you a plot like this at a planetary encounter, this plot would be flat as most of the energy from the flow went into the thermal energy of the particles. Here, very little of the flow energy goes into the thermal particles because most of it's going into the pickup ions, which end up with energies of a few keV. New Horizons, of course, measures pickup ions in a solar wind and has made some very nice measurements. There's no magnetic field to compare with, and it's unclear how far they will get. Hopefully they'll get past the termination shock, but I wouldn't expect them to get to the heliopause. And like as I said, in the heliosheath, most of the thermal energy is in the pickup ions, and these are an important ENA source. So it'll be good to have measurements of these throughout the heliosheath. One puzzle we have in the heliosheath from the Voyagers is the flow pattern. This is something that the SHIELD Drive Center is studying now that Marav talked about on Tuesday, I think. She's in charge of that at BU. Voyager 1, we saw we don't have a working plasma instrument. LACP uses particles to determine what the flow speeds are, and the flow speeds were smaller than expected, below 100 kilometers per second, dropping off about 8 AU before the heliopause to 0 and sometimes even inward. And so that was a puzzle why we'd have the stagnation region there. We got the Voyager 2. The black line shows what the PLS instrument saw, observing the plasma directly, a slow decrease in VR across the heliopause, and then across the heliosheath, then a sharper decrease before the heliopause. However, you can also use the energetic particles to determine the speeds using the Compton getting effect like you did for Voyager 1, and you get things that look very different. Much higher speeds in this region close to termination shock, and here the average speeds are the same, but there's many more oscillations between 0 and 200. And again, about 8 AU before the heliopause, they start seeing a decrease in average speed below what the PLS is measuring. So Alan Cummings written a paper showing that these same Compton getting speeds are seen using the CRS instrument during rolls. So the puzzle is if something about these Compton getting measurements not right, that they're giving us these strange speeds, or something about the PLS measurements. So it'd be good to have another spacecraft going through measuring these flow patterns to see what's going on. The heliopause, of course, Drew mentions a very complex region. We start seeing signatures of it more than AU upstream of the heliopause. You see these increase in galactic cosmic ray intensities at Voyager 1, and also here at Voyager 2. Voyager 2, where you had a plasma instrument, we saw this plasma boundary layer where the speeds went down. This shows the pressure, but the speeds are going down, the density went up, the temperature went up, starting well before the heliopause boundary itself. We also saw a magnetic barrier partway through the plasma boundary layer where the magnetic field went up by a factor of 2. And we saw correlated changes in the energetic particles. They look very much like the plasma profile, and changes in the galactic cosmic rays seem to be associated with the changes in the field. So this would be, we've seen 2 very different versions of the heliopause. Another one in a different region might help us understand what's going on. And finally, the interstellar medium. This shows the currents in the PWS detectors. These are the 3, PLS detectors. These are the 3 cups that are looking sunward and seeing the radial outflow. So you see that at the heliopause, the currents drop to 0, radial flow is gone. In the interstellar medium, we're seeing currents in the D cup, which is looking sideways. We're seeing lots of structure in the interstellar medium. The problem is that we only seeing these currents in the lowest energy channel. So we don't know if these changes are due to changes in temperature or density or flow. So we need to do a much better job of looking at plasma in the interstellar medium, and hopefully ISP can do that. And finally, to summarize, what we need from ISP is another look at regions like the termination shock, the heliopause, the heliosheath, especially looking at pickup ions in the termination shock and the effect they have, the flow patterns and pickup ions in the heliosheath. At the heliopause, at the boundary layers, the magnetic barriers, the GCR increases to see if these are common features at different locations. We need, of course, to look farther out, see how magnetic field changes and is draping away from the heliopause, what the plasma parameters are further out than Voyager is seeing, and also when GCR stop being influenced by the heliopause. And we also need a better look at many things, especially the interstellar plasma, the electrons throughout the heliosphere, the pickup ions throughout the heliosphere, and the alpha particles in solar wind and the helium in the interstellar medium. So that's all. Thanks very much.
John, thank you so much. So I should have said too that what we're going to do with this session is we're going to let the speakers give their talks and then we'll ask some questions. I'll limit the questions after each speaker to just a few minutes so that we give all the speakers a chance to talk, but then we'd like to, of course, carry the discussion on afterwards as well. So that said, does anyone have any questions for John? That was an excellent intro, by the way, John. And yeah, thank you. So I've got one to kick it off if no one else does right now. So John, considering that we have these, we're going to be limited to a single point observation, same as with the Voyagers, basically along a track. Now to study dynamics, particularly along boundaries, these kind of mobile boundaries, what chance do you think we have, or what strategies should we employ for taking these single point track observations and trying to back out everything we can about what that means about spatial temporal nature, and particularly again with respect to boundaries, but as well looking at, say, turbulence along the way, and potential signs of reconnection?
I think the important thing is to be able to get the highest time resolution that you can during these boundary crossings. And if you can record data and then figure out where the crossings are and then play back high resolution data from that, that would be very helpful. Voyager, of course, is limited to this 160 bits per second, and we have data gaps, so we missed a lot going through, and hopefully there won't be a problem with ISP.
I agree. So I think the onboard high rate captures and then the ability to request, chunks of those very high rate data for targeted regions is a very wise approach here. Any other questions for John right now?
Drew,
I had
James here. There's two questions. There's two hand raised in the participants.
Oh, awesome, James. Thank you. Thank you. All right. So first I've got Benoit. Go ahead.
Yes, this is Benoit. So I could see that the energy of the flow is 3 eV or even less, and for the electrons as well. For measuring that, of course, the spacecraft potential is an issue. Do you know what that is?
On Voyager, I don't.
And do we have any modeling that could help us know what it could be with Interstellar probe?
That's probably a question for one of the engineers, or Drew, or not me.
So I guess yes, but that's definitely very important.
It's very important, yeah.
Completely. So
that low energies.
Totally agreed, Benoit. You actually beat me to my second question. That's what it was going to be. Was on the spacecraft charging.
Right.
So does anyone have any comments on that?
We could measure it. We could put a voltage probe out on the boom.
Exactly. Stuart,
Yeah,
I figured you had
so
mentioned something like that.
so it probably means that we have to have very, very accurate high voltage supplies on the plasma instruments. And at low energies, very often it's difficult. So
That's right. I'm wondering too if, I mean, so Benoit, to get to your point, I think yes, we can attempt to model it, right? Obviously, the design of the spacecraft plays a huge role here, in particular the materials that are selected for the surfaces. That said, though, I mean, we have seen architectures before and missions before that do basically they control the spacecraft potential, which may be something we need to look into here as well. But that is an excellent point to raise.
So that being said, I think that John in his slide was showing an expectation that the density would be high. If that were true, then it means the spacecraft potential should be low, which would be an advantage.
That's right.
But if we don't really know what it will be, I guess we have to expect for the worst rather than the best.
We're pretty far from the sun. It's not going to be a lot of photo emission.
That's right, and these are exactly all the factors that I'm guessing why we can actually do some at least reasonable modeling for this.
Yeah, the electron temperatures are very low, so you probably wouldn't expect a lot of charging.
That's right. Okay, so I'm going to go to Parisa. You have a question?
Yeah, hi. This is very interesting talk. I have a naive question. You mentioned that plasma instrument can measure up to 6 keV. So why we are not able to measure keV pickup ions with this instrument?
Well, two reasons. One is that after Jupiter, where the pickup ions started being important, we had problems with some of our higher energy channels due to radiation damage. So we have a fair amount of noise in those channels. That's the biggest reason. The other reason is that the fluxes are low. They would be on the edge of what we could see anyway.
I see, thanks.
And we'll get one more from Arik.
Yeah, thanks, John, for the presentation about what we have already done. I would have liked to see more about what Voyager was not capable of measuring, meaning the composition instrumentation that came up in the 1980s after the launch. I'm trying to gauge the interest in the community about the elemental charge state and maybe isotopic composition of the interstellar medium, which doesn't have a special topic, so it has to be covered here. Can you have any opinion on that?
Yes, it certainly would be nice to have. Very close to the sun, we were able to measure some 06 plus, 07 plus, but only very near 1 AU. It would certainly be nice to have measurements of everything else further out.
Agreed. So if you saw from the slides that I showed, when I showed the spacecraft model, I had those parentheses S for sensors. And this was actually one of the main driving motivators there to potentially stress that we may need multiple sensors, and composition was exactly the reason there. So this is one of the things that I'd like to capture with the discussion on notional requirements for the instruments is what are the most important species that we want to capture. John mentioned, of course, the protons and alpha particles or helium. But we need to start nailing this down and actually prioritizing. I think that's going to be key to the discussion here going forward, and to start refining basically what is possible for the instrumentation that we will be baselining. That'll be critical information or input for a future science definitions team. Okay, so thank you for the discussion. We can move on to the next talk from Matt. And while Matt's pulling up his slides, I'll just say that if anyone else has any other questions on the plasma and thermal particles side, please keep your questions in mind for the discussion after the speakers are done. So Matt, I will let you take over.
Okay, I think I'm off mute. And I'm looking for the screen share. Here we are. Let me do this. Is it sharing my
It's sharing your desktop, I think.
Okay.
Yep, we can see your desktop. So if you
Oh,
go to full screen, that should
All right, because it's not. Yeah, it's not highlighted
full
for
screen
me,
on the
so I can't
PowerPoint.
tell. Oh no. Is it doing that annoying thing?
You just need to swap the views. Yep, it's in the
Uh,
presenter mode.
I'm looking for the swap button.
It's upper left. There you go.
Okay, now we're good.
Yes, looks great, Matt.
Okay, great. Oh, this is annoying because now I can't see people's faces in the bottom there. Okay. So yes, so thanks for asking me to do this. Hopefully I can just shed a little bit of
Matt,
light on.
if you
Oh.
share the screen after you open the windows, you will be able to see us.
If I do what?
If you share your screen
Oh,
after you put the windows up, you can see us.
Oh, okay.
I had the same issue.
So now you guys can't see anything, right? Because I unshared, and now I'm sharing again.
Yeah, now you can see us.
Yep, you just need to swap displays again there, Matt.
I gotta swap it again?
Yep.
Oh, what do you got? All right, let me see, where'd it go?
There we go. Looks good.
All right, well, okay, now it's really weird. Okay, so I'll wow, I'm totally discombobulated now. It's showing me something strange. Sorry. I don't even know what it's showing. I think I'm projecting the.
You're on. It looks like slide 2.
I don't know how that happened. Sorry, something's messed up. Okay, I guess that's good. All right, sorry about that. Okay, so I'm on. Apologize. Okay, so let's talk about energetic particles. Can you guys see my mouse?
Yes.
Swirling around? Okay, good. Now let me get this thing out of the way. Okay, so I want to talk about energetic particles, by which I mean super thermal particles and energetic particles. And I'm including anomalous cosmic rays, and I'm going to touch on cosmic rays just very slightly because Jamie is going to talk about it after me, but a energetic particle sensor will have some things to contribute to that, but it's only going to be a brief touch on that. So let me just talk about the different species. On the right, I have a spectrum at 1 AU from this paper here, where I've marked up basically, here's solar wind going into super thermal energetic particles, etc. I'm showing galactic cosmic rays in purple, anomalous cosmic rays in green. You can't see in this plot, but pickup ions would be over here somewhere in the shoulder of the solar wind. And these are the main populations I want to talk about. I kind of say energetic particles and solar energetic particles. It's a blur from superthermals into energetic particles and what you call solar energetic particles. I'm just really kind of talking about big events that come from the sun, or shocks passing by, accelerating things. And so an instrument like this would cover most of these species. You can see over on the left. Oh Jesus! Excuse me. Pardon me. Over here, you can see this is a composite of a few different instruments and missions, actually, of data, including SWAP data from New Horizons and Cassini data and Pepsi data from New Horizons. But the point is, you can see here is you can see solar wind, pickup ions, and then superthermals and energetic particles. And so there probably would be some kind of overlap between the plasma energy instrument and an energetic particle instrument. Pickup ions and superthermals are extremely important, so it's probably smart to have an overlap to cover them. And next, here is just for reference is the traceability matrix if we need to pull it up. And again, I'm talking about mostly stuff with the energetic particle sensor would measure, with a little bit of overlap science-wise on the other two. and this is also, just for the record, the list of the working STM science questions. Okay, so what I want to go here, everybody's seen this plot before. I'm labeling also slightly different terminology. Outer heliosphere, inner heliosheath, and outer heliosheath, because I want to talk about the different particle populations that we expect to see here in these regions. You can see my abbreviations for picobion, superthermals, energetic particles, ACRs, GCRs, and yeah, I've mentioned this about GCRs, that I'm only barely touching on it. So there's various things we can measure. We can measure species and separate electrons from ions, hydrogen, helium, oxygen, etc. Maybe molecules. Oops. There is the idea of charge state. I don't think we have anything baseline for that, but I wanted to mention that. That is something we could consider. There's energy, direction, intensity, and then from this you can put together spectra, anisotropies, pitch angle distributions, etc. What I want to point out here is that the mission kind of divides up a bit on the science for the energetic particle and superthermal sensor. So what I have down here is the 4 or 5 particle populations, and then just some lines showing where they're important, associated with this logarithmic depiction of the heliosphere. And picobions become more important and easier to measure as you move out. You know, it depends on what's going on as far as activity and this sort of thing. So I sort of showing that, kind of phasing in a bit, and becoming important a little bit further away from Earth. Although we'll be moving pretty quickly, so I guess we'll be getting out to Jupiter kind of pretty quick. So there'll be picobions will be something that we could certainly look at. Superthermals, they're pretty much around all the time. Energetic particles are really the higher energy tail of the superthermals. But then here I have SEPs, just as it's really kind of including CIR remnants and this sort of thing too, but they kind of will peter out a little bit as we get further out. But the reason I want to show this is because you can see that when we're inside the heliopause, that's the population we'll be looking at. A cosmic ray sensor will look at cosmic rays, but that's not the energy range I'm focusing on here. But once we do get past the heliopause, what happens is that most of the populations drop away completely, and we're left looking at the low energy portion of the galactic cosmic rays. And that's what I wanted to highlight here. So I think what I think we want to do is I say expand and improve the measurements and then make new measurements. And so sort of where we've already been out to the very local interstellar medium, for lack of a better term, we're going to want to expand measurements. In particular, we're going to want to go down to lower energies. So right now, with Voyager 1 and Voyager 2, my phone's ringing now. Sorry, I'm getting lots of distractions this time. I apologize. Go away, phone. Voyager 1 and Voyager 2, we do go down to around, I think it's 28 or something keV, also say 30 keV, but without composition. So there's a gap, first of all, between the solar wind that John was talking about and the lowest energy from the LECP instrument. But even though we cover from around 30 keV and up, we don't kick in with composition until more like 300 keV. Pepsi, which I'm also talking about, showing some data from, does do composition down to these lower energies. So that's one of the major expansion will be to not only just go down to lower energies, to go below 30 keV and then hopefully overlap with some superthermal and picobion measurements from the lower energy instrument, but also to have composition as well, and good time resolution and all these sort of things too. So that's an expanded, the improvement is, well, I'm sorry, that's the expansion part would be a whole new population, which is getting down to these low energy superthermals and pickup ions. And improvement would be including the composition, like I just mentioned. And then the new would be the very lowest energy GCRs, which are below the energy that we can measure inside the heliosphere, as we know, because there's other populations there, and also below what Voyager 1 and 2 can currently measure in the interstellar medium. So let's see. So this is a plot showing basically energetic particles as a function of time. This is from 91 to 2000, and ACRs. These are two of the major energetic particle kind of populations, and I'm just showing that kind of as you go away from the sun, you get fewer of these guys, fewer events, and this is also has a solar cycle effect in it too as well. So things are getting quieter, so it's more complicated than this is implying. But also the ACR intensities go up, and I'm showing here on the right just some anomalous cosmic ray spectra. And I didn't really define what anomalous cosmic rays were. Most people here, I think, know, but these are basically high energy particles that are accelerated, thought to be accelerated at the termination shock, although we didn't see them directly at the shocks we crossed. They could be measured, they could be accelerated at other parts of termination shock. Perhaps there's some kind of stochastic acceleration in the heliosheath that accelerates them. But these do change as a function of distance away, and so we should be able to pick that up as we travel out. Here is a discussion, or just a couple plots of in the outer heliosphere and inner heliosheath, where we can look at the superthermal particles and energetic particles, showing the cosmic rays up here, but I'm not really going to talk about those. What I want to talk about is that superthermals, in this case from Pepsi with 2 to 200, above 2 keV per nuke helium, you can see when shocks combine things, you get compressions and you get intensifications, and you also get something in energetic particles. Things kind of quiet out, get a little more quiet as we go out further. Here, there's sort of more activity, more variation, and this is basically looking at this magenta color is looking at kind of this energy range, and in the black it's looking at this higher energy range here, like up to 100 to 100 kV up to an MeV. And then here we'll galactic cosmic rays, we could look at Forbes decreases, and this helps us do things like identify events that go by that are locally accelerated versus residual remnants of things from the inner heliosphere, CIRs and such. What I wanted, let me go back real quick. So if you look at in 2015, towards the end, you see here the spike in energetic particles, and you see a pretty good size increase, intensification here in the superthermals. One thing that'll be important is, compared to the Voyager spacecraft, will be to have good time resolution. You can see here on these are actually two different events, so I apologize about that, but the point is made. You can see here on the right, the spectrograms, we can have pretty good time resolution to see variations. And here I'm showing on the left in time intensity profiles. In this case, it's counts per time, showing like a very narrow spike. There are also some situations where we cross a shock where we'll have variations on the order of tens of seconds, which are narrow structures that'll tell us something about the shock shape, and that's something that we can't see with Voyager, but we could see with Pepsi, and we could see with a new instrument that we develop for a potential interstellar probe mission. How am I doing on time? I've like 5 minutes left.
About
or?
2 to 3 minutes left.
2 to 3 minutes. Okay, so let me. This is more about superthermals and things. Let me just go ahead and skip through this one. Here's a bit more about superthermals. pick up ions we can look at. We can look at the spectral slope of shocks, for example, at the higher energies, to see how they affect and what kind of mechanisms are causing those changes. Let me make sure I touch on termination shock. Here is some data from the termination shock of Voyager 1 and Voyager 2. In the middle is Voyager 1. Here's a spectrum. And the thing it shows that is important is that there is a gap here. I'm sorry, yes, sorry, I apologize. The anomalous cosmic ray peak is here, and it doesn't connect up to the lower energy superthermal or energetic particles. That doesn't happen until further out in the heliosheath. And again, so this was the famous lack of a accelerated anomalous cosmic ray spectrum when we crossed at Voyager 1. I'm just pointing out here a couple things is that we have anisotropy information needs to be gotten. So that's, you know, a spinning spacecraft certainly would help with that. Or, spectral information is very important. If you look here on the right here, you see different energy channels. And before and after we cross termination shock, the spectral slopes change dramatically. You can see they're all over, I mean, they're kind of very widely here, and then they kind of tighten up. So I wanted to show that. Let me skip that since I'm getting low on time. The point I'll make here is just that while we're in the heliosheath, I'm kind of moving out in radius, if I should have mentioned before to guide you guys. That we have lots of different species. Here I'm showing, and here's showing from like 40 keV ions. We'll be able to go lower with a newer instrumentation up to tens of MeV. And for example, here, when we interact with the edge of the sector zone in the current sheet, we have different behavior that'll be nice to also to see additional measurements from. So let me, I got like 2 more slides, I think. So here is Heliopause measurements. And what you can see is Voyager 1 on top and Voyager 2 on the bottom, where you have galactic cosmic rays, and these guys increase. And as we cross over these regions, the GCRs kind of spike, and then they come up to the local, very local interstellar level. The heliospheric particles do the opposite, basically. The electrons peter out very early, relatively, and then the protons, in this case, we were talking about like few MeV particles, and then these are lower energy ions as well. They drop off and really peter away to background kind of levels as you cross. And there are different structures. There were different features at Voyager 1 versus Voyager 2. And here's just some detailed anisotropy kind of information. But I won't go through that in detail. I guess I'll mention this is the cosmic rays, and we'll hear more about that in a moment. But this is anisotropies are important at the high energies for cosmic rays, but also at the lower energies for looking at heliospheric particles, superthermals, energetic particles. So the final thing I'll say is about the transition from when we cross the heliopause, from measuring the heliospheric particles to cosmic rays. On the left here is some LACP measurements from Voyager, and you can see what happened is that on the inside of the, before we crossed the heliopause, we had spectra, look at this one here, that were roughly power laws dropping. These are superthermal particles. And then afterwards, we had these edges of the galactic cosmic rays. The CRS instrument on the right is designed for measuring cosmic rays and has a larger geometry factor, et cetera. And you can see a nice spectrum that's collected here that Alan published in 2016. And the thing I want to mention is that it was already, before we left into interstellar space, you know, the galactic cosmic rays, you couldn't really see them below you know, 100 MeV or, you know, at least tens of MeV, but like roughly 100 MeV or so, you couldn't look at the galactic cosmic rays at all. So that opened up right here. So all this stuff here is brand new that we wouldn't be able to see before. But additionally, with an interstellar probe, I wanted to point out here, and I think this is my last slide, that this is sort of where the cutoff is for CRS instrument that I was just showing from Cummings' paper. Now we'll be able to go down another couple orders of magnitude and see the galactic cosmic rays. And I think this is important because the galactic cosmic rays in this energy range, going down to like, you know, 10 keV or something, are going to be probably the most sensitive to variations, and they're dealing with the most local transport. The higher energy particles can penetrate in more easily and are less affected by the local structure of the medium. And so, yeah. So when we get to this part of the mission, we'll turn into a lower energy cosmic ray instrument, and then of course, if there's any surprises out there, we'll still be measuring particles of all sorts. So you know, we could see something that surprises us, but this is what we would expect based on Voyager. I guess I'll just end on this slide. Excellent. Here.
Thank you, Matt. So let's just transition right into Jamie's talk on cosmic rays. So if anyone has any questions for Matt, please hold those towards the end. Jamie, you want to pull your slides up, and I'm just going to use the time to reiterate a point that Matt made that I think is really important here, and that's to stress that overlap between instruments is really important here. One, we get to intercalibrate between them, which builds confidence, of course, in the data products from both instruments at each overlap. But also, you basically are doubling up on the data in that overlap region, which is also beneficial from the analysis standpoint. Okay, and Jamie, looks like you're up, so I will just hand it off to you.
I have to unmute myself here.
There you go. And we just lost your slides too. They were up, but now.
Yeah, that's all right. I'll share. No worries.
Okay, great. Thanks, Jamie.
All right. Does that look good? Does that look like it's presenter view, or?
Yes, that looks great.
All right. So first off, thank you so much for the invitation to give this talk. This is a great honor to be thinking about these things. But first off, just a quick overview, like who am I and why am I here giving this talk? Briefly, I joined the Voyager team relatively late in the game. And so most of my focus is going to be on galactic cosmic rays here in the interstellar medium. We call it the very local interstellar medium. And in interstellar probe parlance, that's just beyond the heliopause in the outer heliosheath region. And so I joined relatively late in the game, but I will forever be grateful for the stunning opportunity that I had to see Voyager make history. I started working for Ed Stone at Caltech 5 days after Voyager 1 arrived in the interstellar medium. And in fact, my first day on the job was watching at the science working group meeting, discussing those results and trying to interpret the data about crossing the heliopause. So it's amazing. And this is all to say that we truly stand on the shoulders of giants here. But at the same time, I have some challenging things to say that I hope Interstellar Probe will consider. And I hope at the very least that it will lead to some lively discussion. So I'm gonna give a brief overview of some major milestones, discoveries, takeaways from Voyager's observations of galactic cosmic rays out in the very local interstellar medium. And then after this brief overview, I'm going to start delving into ideas about instrumentation and science opportunities for Interstellar Probe. So without further ado, let's see, it seems frozen. There we go. So anyway, this is all to summarize that Voyager spent quite a lot of its time in the heliosheath. It spent 35 years for Voyager 1, 35 years or so, Voyager 2 longer. But they, even here, they saw the region as the neighborhood of the outer planets, and then the outer limits of the sun's sphere of influence, wherever that is, and possibly beyond. So, you know, as the Voyager mission was traveling out, they didn't know where any of these boundaries were, and we're thankful that we crossed them. But a lot of it's important. It did a lot of very important measurements through the heliosheath, and I think Matt, or through the heliosphere, and I think Matt covered that very well. But I'm not going to cover that here. I'm going to cover basically the big takeaways we learned from interstellar space. So I think one of the coolest kind of accomplishments, though, is the history plots. Just like John showed the history of the plasma measurements, this plot of cosmic rays from Alan Cummings' 2016 paper is probably my favorite, that just shows a snapshot of cosmic rays through the entire heliosheath. So we see at 1AU, you see the effects of solar modulation pretty strongly. You also see this radial gradient occurring. And the solar modulation is more prominent, it appears, in these greater than 70 MeV cosmic rays, more prominent towards, you know, in the inner heliosheath. But then after crossing the termination shock, you know, you don't see these effects hardly at all, these effects of solar modulation. But you do see a stronger radial gradient. And then at the crossing, the heliopause is quite an abrupt transition, startlingly abrupt. And then the interstellar medium. And the interstellar medium is surprisingly quiescent compared to the rest of all of this that we have seen. So there's a lot of filtration, a lot of modulation of cosmic rays through the heliosphere, but as Matt pointed out, out in the interstellar medium, things change a lot. So another really important, I think, Voyager takeaway is that, as Matt also described briefly, is that the lowest energy cosmic rays we have a good spectrum of these lower energy cosmic rays and that have been measured before. Typically, most cosmic ray studies that do serious cosmic ray measurements in ground-based observers or even in space, they're considering cosmic rays of GeV. So at the abrupt, here's the spectra from their most recent Stone et al. 2019 Nature paper about Voyager 2's crossing, but here's the spectra that's overlaying Voyager 1 and Voyager 2. And in red is Voyager 1, blue is Voyager 2. The spacecraft are very different location, and the spectrum agree quite well. And it was a question before the crossing of whether or not we would immediately see unmodulated spectra. But there are a lot of indications. Of course, you know, we're not that far from the heliopause boundary, but there are a lot of indications that this is most likely the pristine interstellar spectrum. There was a really abrupt transition at the heliopause. There's remarkable consistency of the two spacecraft despite their very different trajectories. And there's not really any signatures of solar modulation at 150 AU and counting. So, you know, maybe it's a locally unmodulated spectrum, but so far it looks like it's just unmodulated. And another really interesting point that I think Voyager made is that there's actually greater intensity by at least one order of magnitude, maybe 1.5 orders of magnitude, greater intensity of electrons below 40 MeV out there. So and Cummings et al. Found that this electron spectrum was consistent with the solar wind observations. But that's also an important science takeaway, is that the intensities of electrons are higher intensity. So it'd be very interesting to see what happens, how this spectrum continues down here for the electrons in particular, I think. Now, a third big contribution discovery is the galactic cosmic ray anisotropy. And this is my personal favorite, simply because this was a topic of my thesis, but LECP discovered this first upon the crossing of the heliopause. They discovered that in their sector, looking perpendicular to the magnetic field in blue, they discovered these pretty uniform in the other sectors, but but time varying intensity changes in just mostly in this sector that's perpendicular to the magnetic field. And these are kind of unusual because they're pretty smooth changes over time. The effect in the second panel, this is a CRS view of it, the omnidirectional telescope. So we didn't distinguish directions here in this panel, but the effect in the omnidirectional intensities is very small. It's only about a 3.5% if you take the deepest ones of these. So we have these paradoxically long-lived events, but they're very low intensity change. So how do they exist? And this is just a testament to the fact that the interstellar medium right beyond the heliopause boundary is a lot less turbulent than anything that we've seen so far. And a part of my thesis work is kind of illustrated a little bit in this bottom panel, where this telescope, this body fixed telescope of CRS telescope, it's looking kind of stuck looking around like the green and red sector about 30 degrees off the magnetic field. So we didn't really see, we saw these kind of particle intensity modulations due to shocks. We didn't really see the effects of the anisotropy except these times right here, these little dips that we can see. And those are spacecraft maneuvers that allowed us to roll and temporarily view the pitch angle anisotropy. And using these spacecraft maneuvers, I was able to confirm that, in fact, this anisotropy is centered at 90 degree pitch angle, and it affects particles within about a 22 degree wide region centered about 90 degree pitch angle. And it's about like a 15% of the overall particle distribution appears to be affected to account for our observations. And we also made a further important and interesting discovery that we recently published. And that is that this anisotropy is species dependent. So black here, this is gray, this is that same omnidirectional proton observation. Black here is just during certain roll maneuvers on our directional telescope. And then red and green are electrons. So the first question is, well, if we're comparing the electrons with galactic cosmic ray protons that are greater than 70 MeV and it's an integrated rate, is this an energy effect or is this a species effect? Well, it turns out that if we look at our lower energy protons, we actually do see very similar time varying signatures as we do for our high energy protons. So if we compare like the 5 to 100 MeV electrons and the 18 to 70 MeV protons, that kind of takes out questions about energy difference. It could also be a telescope effect, but it turns out that this green and this blue are the same sides of the same telescope, and they're looking at the same direction, obviously. So here, these electrons don't see it. And then we have a third dedicated, completely dedicated electron telescope that not only looks at kind of 5 to 105 MeV electrons here, but it also looks right at 90 degree pitch angle when these roll maneuvers are happening, these spacecraft maneuvers. In this case, these are 70 degree offset maneuvers where the spacecraft just clocks 70 degrees and just sits there. During this time, the telescope's bore sight is looking directly at the notch of the affected kind of distribution of particles where the intensities drop out. And so we should see a stronger, if not, probably a stronger effect in the electrons if this were not species dependent, but we don't. So that was, and there's a lot of papers coming out, I think, that are looking at why this is, but it was a cool discovery. It's a species dependent anisotropy. Another major kind of takeaway from the Voyager observations is the discovery of these transient events in the very local interstellar medium. And this plot right here definitely highlights the need for multiple types of observations that tell a complete physical story. So here on the top is the magnetometer measurements, and you see these forward and possibly reverse shocks that occasionally pass Voyager. And preceding these shocks, there are energetic, like particle shock spikes, basically, as sort of precursors to these shocks passing us. However, they don't always happen. We can observe shock spikes remotely, even if the shock doesn't cross Voyager, because we're just seeing energetic particles that are connected to the fill line of the shock and flowing back towards us. And so we see these shock spikes, and we also see these electron plasma oscillations. And it occurs all in the right sequence according to Don Garnett's hypothesis that you'd have the highest energy particles accelerated first to the shock front. So they're traveling the quickest and you'll see them first, and then you'll see these lower energy plasma oscillations from these electron plasma beam instabilities, and then the shock will cross Voyager. And so it's just, and every one of these is kind of representative of some sort of transient event that has basically caused some sort of pressure wave to cross into the interstellar medium, most likely related to solar activity. In fact, we can see directionality, and it is from the sun outward direction. So this discovery of these transient events in the local interstellar medium also somewhat surprised us, because our sun, even though we're beyond the material plasma boundary and energetic particle boundary, the sun is still influencing this local environment in surprising ways. And we had a snapshot of this that was a pretty fun opportunity. Basically, we saw one of these transients, which John Richardson previously wrote about pressure pulses in the heliosheath being drivers of these sort of transient events. But turns out that one of these actually was highly correlated. One of the changes of cosmic ray intensity profiles in the heliosheath at Voyager 2 was really highly correlated with the first event at Voyager 1. So there is 91.2% correlation, very similar time scales that the event evolves. And from this, we actually got a timing between this event as this pressure wave propagated through the heliosheath and disturbed cosmic rays, and then it pushed on the heliopause and transmitted a pressure wave across the into the interstellar medium, and it affected these cosmic rays in a remarkably similar way. And we, as a side effect of this, we were able to use the speed basically of travel, and use Voyager, take advantage of Voyager 2's plasma measurements, and derive a notional effective total pressure in the heliosheath for certain values, just assuming values of temperature in the very local interstellar medium. So if, for example, the temperature in the very local interstellar medium is 20,000 Kelvin near the nose of the heliopause, then we would predict, based off of this event and the travel speed, because we have the timing of this event, we would predict a total effective pressure of 270 femtopascals. And if you break that down, it becomes an interesting exercise of breaking it down to what can be measured right now, which we're kind of, there's kind of 18% that we can't account for at the moment. So like IBEX pickup ions, they make up 45% of this 270 femtopascals. Magnetic thermodynamic pressure makes up about 15% of this probably, and then ACRs, GCRs, probably 22%. This could be electrons. Nobody's really measured the pressures of electrons through the heliosheath, for example. But that was just a fun opportunity that we had, because we had this event that passed from Voyager 2 to Voyager 1. But I think probably the most important takeaway from all of these Voyager pictures of galactic cosmic rays is the snapshot from the outside in. So we've been studying particles, energetic particles, from the inside out for the whole of human history until late 2012. But now we're looking now at ourselves back from the outside in. And it's this cool meta concept, just like the pale blue dot meta concept of Voyager. Now we're like outside of our heliosphere looking back on ourselves. And it's neat that we can have these snapshots. For example, this particular event also enabled us to just take an instant moment snapshot of here we are in the local interstellar medium, here's the cosmic rays, here's the magnetic field strengths. We could compare ourselves to the heliosheath. And we could see a lot of interesting, it brings up a lot of interesting questions about what changes across that boundary. For example, despite these cosmic rays being very, very, very similar profiles in their disturbances, the ones in the heliosheath are isotropically affected. So there's an anisotropy that occurs in the interstellar medium that's not in the heliosheath, even though the pressure profiles of these events look very similar. So, or the time profiles look very similar. So, you know, there's a lot of interesting questions that have arisen from Voyager observations. And a lot of that has to do with the fact that we're looking now from the outside in, and it's a lot different than we thought from that vantage point. So there's many opportunities for interstellar probe. We can watch the heliosphere evolve under very different solar conditions. We can monitor space weather through the heliopause and even beyond. We can provide in situ context for global observations, but there's a really big question here for interstellar probe. Why be like Voyager? There's actually a lot of disadvantages for trying to be like Voyagers. For example, if we consider interstellar probe's speed, Voyager's traveled 14 for Voyager 1, 17 kilometers per second for Voyager 2. If interstellar probe is traveling 5 times the speed of Voyager 1, we need to consider the propagation speed of these events in the very local interstellar medium. A lot of these transients, we deduce speeds of 40 to 60 kilometers per second for these events. Well, if you have a spacecraft that's traveling at 80 kilometers per second, will you actually ever see a shock wave overtake interstellar probe? I mean, interstellar probe will be overtaking all of these events, but there might be some point where it's just too fast. Another thing to consider, especially, mostly I'm focusing on galactic cosmic rays here. Another thing to consider is the fraction of time that will be spent in the heliosphere versus the fraction of time that will be spent in the very local interstellar medium. You know, it's a question of, if we want to measure galactic cosmic rays very well, you know, there's trade-offs between time resolution of those particles and species, for example. And, you know, will we really get that much better measurements if we're crossing these boundaries in fractions of a day compared to what Voyager did? You know, there's a challenge there to address. And then a lot of the science done through the heliosheath, and especially with galactic cosmic rays, was really helpful because there's 2 spacecraft. So the big question that I'm throwing out there is, why be like Voyager? So I'll just really briefly just give an overview. Yeah.
Jamie, I'm sorry to have to cut you off, but we have to give Vladimir a chance to speak. However, I just got a green light that what we can do is we're going to let Vladimir speak. We'll then take a 5-minute break for everyone, and we're going to keep this Zoom session open. So after Vladimir's done talking, we'll do a 5-minute break for the whole group, and then what we can do is reconvene. I really want to hear what you have to say here. So if nothing else, you and I can just talk about this, but hopefully some other people will stay on, and we'll actually do the open discussion at that point. Just to note, though, we will be bleeding into the astrophysics discussion. So for anyone that's interested, you'll have to make up your mind on which one to focus on. But we do have permission to keep this discussion going longer for anyone that is interested, like me. So Jamie, thank you. I'm sorry to have to cut you off. I'm a really bad timekeeper here, but I'm also intrigued and just floored by everything you guys are showing. So I wanted to let everyone speak. So Vladimir, I will pass it off to you. And like I said, we'll take a break after Vladimir's done speaking, and then we'll come back and we'll talk more open discussion format.
Drew, real quick, I'm going to stop the recording and then have you pick it up. So I'm going to
Sure thing.